All right. So we talk about wave interference. Now, wave interference can happen in a couple of ways. So, looking just at the image here, right, where you see those little rings, so from raindrops, from water droplets, and you can see that the waves interfere with each other. So they interfere in one of two different ways, what we consider constructively and destructively. So when two waves hit at, and then we call it in the same phase, they hit constructively, they actually amplify, they add to the wave, right? And when they hit what we consider destructively, it actually takes away from the wave. So we can see it in the image here, where we're going to look at this, and when two waves are in what we consider the same phase, that it will add to that wave. We can see it here, the blue, right, and the black one, and it adds to that wave. And here it detracts from it. We see right there where that we're looking at the black line, where here constructively and destructively, where it hits a node where that blue and black line meet there. So this is the interference when we talk about wave interference, uh, in two different ways. So the double slit experiment was done by Thomas Young back in the 1800s, and when he put light through a small hole, right? Um, how are these light waves going to behave, right? And we kind of get this little ripple effect going across. So once these light waves penetrate that slit, we see these curved lines here, and this creating some kind of wave that extends outward. And then he thought, like, well, what if I make another slit? If I make another slit, and they call this the double slit experiment, what if I make another slit and the same light wave goes through both of those slits? How are these light waves going to interfere with each other, right? Constructively, destructively. So what happens is it ends up looking like this. And the black portion here, the black portion are the nodes. These are the light waves interfering destructively. And then the other portion is where the light waves are adding constructively. And what they do here is, we'll see it on the backboard here. So when these light waves go out and they interfere with each other, is that we get no light where they hit destructively, right? Those are the nodes there. We see these bands of light here. And they do get weaker, like the most intense is the one in the middle. And then gradually, as it expands out, is they do get dimmer and dimmer and dimmer and dimmer, right? But we can definitely see the nodes here from that destructive interference. And we don't see that with the single slit, right? That's only seen with a double slit, because this is where we're seeing interference, right? We put light through just one slit, there's no wave interference until we add a second slit where we're adding in more light. So we know that we've seen light, we've treated light as waves, we've talked about it as particles, and we know that particles do have mass. So de Broglie helps us understand, from wave-particle duality, on how to make more calculations using matter and calculating the wavelength of matter that is moving, right? So here we have wavelength. Wavelength is equal to Planck's constant over momentum. And that momentum is equal to mass times velocity, right? Mass times, that's not frequency there, that is velocity. So we have another formula here where wavelength, they're just inserting it, right? We're just substituting P here, and putting in mass times velocity. So we can actually calculate matter as a wave when it is in motion. So doing this, we can actually find the wavelength of an electron. So that's what we're going to calculate, the wavelength of an electron with some certain amount of kinetic energy. And we're going to have to bring back some of the formulas that we learned last week. And the first half of this chapter is dealing with all these formulas. And again, as a reminder, we're using formulas in other formulas. Right? We're using definitions in other formulas, and we just did it here, is that here's my formula, but I have to insert this formula into that formula. And now we're going to take this formula and insert it into another formula. Okay? So I did give you this one last week, and remember that this is the same thing as E sub k, right? That's still equal to kinetic energy. Kinetic energy, they're the same thing, right? But here's our formula. Kinetic energy is equal to 1/2 times the mass times the velocity squared. So if we can calculate the velocity, right? If I have the kinetic energy, how am I going to go about calculating the velocity? Well, we use this formula here, and once we have the velocity, well, we know the mass of an electron, we know Planck's constant, is we can calculate the wavelength there. So the mass of an electron, right? 9.109 times 10 to the minus 31 kilograms. And I did show you how to rearrange this into, or how to rearrange it in order to calculate velocity, right? So we're going to take 2 times the square root of 2 times the kinetic energy divided by the mass of that electron. So we input that, right? The square root of 2 times 2.56 times 10 to the minus 27 joules divided by 9.109 times 10 to the minus 31 kilograms. And remember, just as a reminder, joules is equal to kilograms, meters squared, seconds squared, right? So where this kilogram, right, gets this kilogram, and then we're going to get the square root, and we're going to end up with units of meters per second. So if somebody can calculate uh, just what this answer is. Mario, what did you get? Everybody should have a calculator. Yeah, 75. And that's the same thing here, Catherine. So yeah, that's a good calculation. So 74.97 meters per second. So now that we know the velocity, right? Now that we know the velocity, is that we can calculate that wavelength. So here we're just going to input this. Here's our velocity. We know what Planck's constant is, 6.626 times 10 to the minus 34 joule seconds. We know the mass of an electron. So here, this is Planck's constant, is the mass of an electron. Here is our velocity, and we'll go ahead and calculate that out now. Mariano, what did you get?
So equal 9.70.
9.70. Did you end up getting this portion too?
Oh yes, times 10
Okay,
to the
perfect.
-6.
No, no
Sorry.
problem. Right, so good, yeah, good answer. 9.70 times 10 to the -6. Did anybody get this answer here? If you
Yeah,
do, I just
I did.
you did.
I
Okay,
did.
so what happens here is that this, when you're doing this in one calculation, and that's perfectly fine. I do it in one calculation. It's just it makes so much more sense. But when you see this multiplication sign here, remember that this is in the denominator. So when it's in the denominator, I want you to think of this. So even though this says multiply, I want you to hit the divide button again. So you're going to input this, divide by this, and then ignore this and hit divide again. Why? Because it's in the denominator. So try that out and let me know, and let me see if that
Yeah,
fixes
it
it.
worked. It worked.
Perfect. Okay, so just kind of remember that, right? Keep that in the back of your head. If it's in the denominator, I got to divide, even though it says to multiply. Okay, but that I'm glad that that's fixed now. So here, matter that's in motion, right? This is making a wave, right? So when playing tennis, these guys hit these tennis balls about 150 miles an hour. We're going to calculate that wavelength associated with that. So in kilograms, that's about how much a tennis ball weighs, 6.0 times 10 to the minus 2 kilograms, traveling at 68 meters per second. So this is going to take quite a bit of work here, right? Or no, actually, you know what? No, I don't think this, no, that's another calculation we're doing later today. So here, right, we know Planck's constant. Here's the mass. This is mass. We calculate this. This is our velocity. So we can simply just plug all of that in. Oh, right? Here's Planck's constant. This is our mass. This is our velocity. And remember that trick? And what answer do we get there?
One 1.6 times 10 to the 34.
1.6 times 10 to the minus 34, right? And remember again, we are canceling this out because remember joules is equal to kilograms meter squared per second squared, which means kilogram goes away and this goes away. I'm going to cancel one of those out. Uh, that we end up with just something in meters here. All right. So moving on now. So we're a lot of concepts that are going to be that we're going to talk about now. We'll get into calculations again in just a little bit, but we got to get through these concepts here. That sunlight is composed of a bunch of light, right? We call white light, right? So it's all the lights. It's red, blue, you know, all the colors are used and recombined to make white light from sunlight. Right? Now, when the colors of light are different wavelengths, and these comes from the electrons that either absorb this light, or I'm sorry, this energy, or they release this energy. Right. So we get two kind of different patterns here. So what happens is every single element has its own what we call line spectrum, right? Where here is just gas, right? This is just gas, and we put an electric charge into that gas. And what happens with that is that when we put an electric charge into the gas, it excites those atoms. When it excites those atoms, it will reflect, or I'm sorry, yeah, it will emit some kind of radiation. And if it goes through some slit and it hits a prism, it spreads out all of those light waves, all those different frequencies of light, those different colors, like because every color has its own frequency, and we collect what's called a line spectrum. A line spectrum will look like this. This is one way it can look, but there's two different emission spectra that we get from this. One is called an emission spectrum, and the other one's called an absorption spectrum. So if we take a look at this here, right, and we see this mark here, and this mark here, and this mark here, this mark here, look at what here are the same marks, right? One of these is called an absorption spectrum, and one is an emission spectrum. An absorption spectrum happens when an electron absorbs some energy, and this is reflected. Um, an emission spectrum is when an electron releases that energy, that frequency, and this is what happens. So I have a pretty good image that kind of explains this a little bit better. So an absorption spectrum, if you're looking at the electron, which is yellow, it hits the orange arrow, right? So when it hits that orange arrow, think of that orange arrow as some frequency, some light wave that's that particular color, right? So here, that electron that's yellow is going to absorb this orange light wave. And when the rest of the light hits that spectrum, that color's missing because the electron absorbed that particular frequency. And for the emission spectrum, it's just the opposite. It's going to absorb that light here, but we're not collecting all of that. We're just collecting what energy came from that particular absorption, right? It's now going to release it and emit that energy. And that's how we can see that orange line there. So here it is again. It's going to absorb that frequency. It absorbs that light wave right there. It's going to release it shortly, and we're going to collect that, and we see that as the emission line spectrum. Right, so that's how we get those different ways. So here is absorption, and here is our emission spectrum, where we're having that because we only excite these electrons for just a short time before they release that energy. They don't hold on for it for too long. So quantum mechanics versus classical mechanics. When we talk about classical mechanics, would have you think that these electrons that revolve around the nucleus of an atom, is that classical mechanics say that eventually that electron is going to get closer and closer toward the nucleus and hit the nucleus. But that simply doesn't happen, right? And Niels Bohr was like, no, 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 like quantum mechanics is different. Quantum mechanics will let us understand that these electrons only occupy what we consider certain orbits, specific energies, right? Is that these electrons can go from one orbit, one specific energy, to another orbit of another energy, right? So, and nothing in between, right? And that it won't hit the nucleus, right? And that's what kind of quantum mechanics explains there. And it's not going to spiral and hit the nucleus. Is that there's specific orbits, specific energies here. So here, um, when that electron is on the inner orbit, that's what we consider the ground state. right? It's not until it absorbs energy that it goes to the outer one, right? It releases the energy, absorbs the energy, releases the energy, absorbs the energy. And there's nothing in between. It's not going to ever be between those two particular orbits, right? And it's like a ball falling down the steps, right? If you roll a ball down the steps, it's never going to get stuck here, right? It's never going to get stuck right here, right? It's always on every specific step that that ball is going to land. And the same thing happens here with these electrons, is that they can either gain energy or they can release energy. So what we have is when it's on here, this is what we call the ground state, right? When it's on that inner circle, that's the most stable, that's the lowest energy state of the particle, right? Um, is when it's in that ground state. We can't excite them, right? And that's what we do for these line spectra, the emission spectra, is that we add energy, because if we go back here, that's what we're doing here, is we're exciting them. We're putting some voltage through that gas to excite them, and then collecting that information, right? So if we add energy, that excites it, and then we have what's called an excited state. And then we have the electron transition, right? That's the movement from one energy state to another energy state. How do we know the electrons are in these locked energy levels? Is that we know this we'll talk about it in just a little while, but we know that they're in these different energy levels from Schrodinger's equation, right? That if electrons were not in these discrete levels, is that then classic mechanics would be correct. And all of these electrons would be traveling around and eventually hit the nucleus, and that particular atom would be no more, because eventually all the electrons would collapse and they would all hit the nucleus, every element, and the element would no longer exist with all the electrons hitting it, right? So this plus Schrodinger's equations, where we can graphically look at what we're going to call probabilities, right? Is that I'll explain it in just a little while when we get to Schrodinger's, but we don't know the location of the electrons, right? We know a general idea of where they are, but we don't know exactly where they're at, right? We just kind of have just some probability of it, and we can see that graphed out, right? But that is more advanced, and that's talking about physical chemistry. So if you do take physical chemistry, you'll definitely get into that if you're furthering your chemistry education there. Um, so these energies, right? So Bohr was able to calculate these energies of these electrons in these specific energy levels. So we are able to actually calculate that, right? Where they are in these discrete levels. So when we calculate those, we're actually going to talk about, so here, if we take a look at this one more time here, the ground state has one energy, and the excited state has a different energy. So there's actually some change in energy as it goes from ground state to excited state to ground state. There is some change in energy. All right, so here n is equal to what we call, that's going to be what we call the principal quantum number. And n has to be, n cannot equal 0, first off. There is no 0 for the value of n. right? N has to be some positive whole number. Positive 1, 2, 3, 4, but always positive and always some whole number. It's not 1.5 because when we're looking at these energy levels here, these locked energy levels, is that there's nothing in between here, right? So we have to have, so we can consider that inner one. So we'll consider this one n equals 1. Now n equals 2. N equals 1, n equals 2, right? And we're going to look at those energy levels that we, so n is the distance away from the nucleus, right? And that's what we consider that principal quantum number. Just how close or far away is that electron to the nucleus? And Z we already know. Z, that we've already talked about this. I expect you guys to remember that. Z is simply the atomic number. If Z was if we were talking about hydrogen, Z would be equal to 1. If we're talking about helium, Z is equal to 2. How do I know that? Because 2 is the atomic number of helium. So we know that. And then Rydberg's constant is, in fact, a constant. This number will not change, right? We're talking about Rydberg's constant. So, again, the excited state, we're going to have N is going to be a larger number in the excited state, right? In the ground state, it's going to be a lower number than the excited state. So we're talking about change in energy. Anytime we talk about the change in energy, the change in anything, we talk about change in volume, final minus initial, change in temperature, final minus initial, change in energy, final minus initial. So here, n is our quantum number, but if we're talking about energy final, energy initial, is that we can actually just use this. If this is our equation for energy and I want to know energy change, then if I want to know the final energy, we can calculate using this. The final energy is equal to Rydberg's constant times the atomic number squared over 1 divided by the principal quantum number, the final principal quantum number squared, right? And then we could do the same thing for the initial. So we have initial, and then we can plug it into. So now we're able to calculate change in energy from final to initial. If I just replace this here and replace this here, we get this formula. And I'm going to clean it up. So here it is. So you don't necessarily have to write that one down. But here we have energy, right? And again, we can simply just write this. Energy is equal to negative Rydberg's constant, z squared, 1 over n squared final minus 1 over n squared initial, right? This is in here because, well, why? Energy is equal to Planck's constant times frequency. Right? This is not velocity. This is frequency here. That's why. And then we could just say, well, the change in energy is equal to Planck's constant times frequency. Right? Books use two different formulas. Right? Both formulas work the same. If we perform a little bit of algebra to this, we get this. Right, where we can actually draw out the negative here, but now it's going to be initial minus final. That's the only change there. But it doesn't really matter to me which one you use. Your answer will be delta frequency. Yeah, this delta. Oh wait, here. No, this is not delta frequency. This is change in energy is equal to Planck's constant times frequency. Does that answer your question, Ian? Okay. So here, it doesn't matter which one you want to use. Your answer is going to be the same. Okay, so again, whichever one you like to use. Most of the time, this is the one I use. That's the one I'll probably provide you for the exam. Now, when we're talking about the energies here, if we're looking at this image still, well, you can kind of you kind of know you're doing the calculation correctly whether your answer is negative or positive. And if you get a negative answer, don't be worried that you calculated it wrong. If you get a negative answer, it's because you released energy to the surroundings. You went from N2 to N1 or N5 to N2, is that you release some amount of energy. When energy is lost to its surroundings, that's what we consider negative energy. That's spontaneous. It's spontaneously going to occur that this electron will emit that energy and go back to the ground state, right? So when your initial quantum number of n is greater than the final quantum number of n, energy is lost to the surroundings and the change in energy is negative. Right? Change in energy is positive if your n initial, if the initial value of n is less than the final, right? And then we're going to have some positive energy. So let's go ahead and let's now make a calculation using this. Oh, sorry. I guess we got to go over here. So let me write this down here. Visible light. We use this. This is what we call the Bohr series. There's different series as far as calculating um, these energy levels. So Lyman is in the ultraviolet light spectrum. We don't see that. The Passion is an infrared, and then Bracket is like higher end on that infrared band. And what we see is the Bohr series. So it, for the Bohr series, these are n. So this is n equals 2, n equals 3, n equals 4, so on and so on. And you'll notice something here that the Bohr series, n is not less than 1 or not less than 2, right? N cannot equal 1 for what we consider visible light, our Bohr series. Right? And this is the one where we're going to be making calculations. I need to let you know, I'm letting you know aware that there are other series, but for here, we're just going to talk about the Bohr series. And it's important to remember that n equals 2 is the lowest value of n for visible light. The other thing we need to notice here is that we don't have to go from one energy level to the next energy level to the next energy level to the next energy level. Is that an electron can go from n equals my mic kind of n can go from n equals 8, n equals 7 to n equals 2. Right? N can go from n equals 2 to n equals 4, right? N can go from 6 to 3, and go from 5 to 2, right? It doesn't have to go simply step by step by step by step, okay? So using all of that information now, right? We have to remember this that I gave you last week, that frequency is equal to the speed of light over the wavelength. We have to remember that energy is equal to Planck's constant times, I'm sorry, not but frequency. So energy is equal to Planck's constant times the frequency. And that if we have this information here, if we know the quantum number, the principal quantum number, we can calculate energy. And if we can calculate energy, we can calculate its frequency, and if we get its frequency, we can calculate the wavelength. So we can understand what the wavelength, or calculate what the wavelength is, simply by knowing some principal quantum numbers, right? Again, right, we need a formula to put into another formula to put into another formula. So here we're going to simply replace, right? All we did was we took this and replaced it, right? Now, in order to calculate wavelength, well, that needs to be rearranged now, right? So if we rearrange that, we end up with this formula here. So wavelength is equal to now Planck's constant times the speed of light divided by the energy we get from calculating it from these two quantum numbers. Now, my initial is 5 and my final is 2. That we are going to lose energy to the surroundings. Is my change in energy negative or positive?
Positive. Negative.
Negative. If an initial is greater than an final, right? That's what we're gonna lose energy to the surroundings. So that's just, if we lose something, we're kind of, they may think we're going to be negative, right? So maybe just kind of a little reminder on that. But good concept question for an exam. Hint, hint, right? So here we are going to have some negative energy here. All right. So knowing all this information, right? And here it does say hydrogen atom, and that's going to be atomic one. I didn't put it in here, but you guys can do it. I just don't do. It's just an extra step. I'm not going to do the square root of. I'm sorry. I'm not going to do 1 squared. But if you wanted to, fully write this out, it'd be 10 to the minus 18, and this should be joules. I should have put the units in there. And then we did, times 1 squared, 1 over 5 squared minus 1 over 2 squared, where this represents the, but it's going to be the same answer. I just didn't put in there because it's 1 squared. All right, but our answer is in joules here. So if you can calculate, somebody can calculate what this energy is of a hydrogen atom going from N5 to N2.
I got negative 4.578 times 10 to the negative 19.
Yep, sounds good. I like it. That's what I got too. All right, so negative 4.58 times 10 to the minus 19 joules. And this value can now be put in there. We know what C is. C is 3.00 times 10 to the 8th meters per second. We know what Planck's constant is, 6.626 times 10 to the minus 34 joule seconds. And we plug that in. Here's H, right? Planck's constant. This is the speed of light. This is our change in energy. And this is our conversion because I did ask for it in nanometers. So we have our conversion there in order to calculate that out. Right? Joules cancels joules. Seconds cancels seconds. Meters cancels meters. And some answer in nanometers here. And something interesting will happen on this after this calculation. And I love this example, by the way. Another this seems like a great short answer question because there's a lot going on here. Yes, negative 434 nanometers. So that's exactly what we get there. Now, the interesting thing here is this is length and this is negative, right? we have a negative wavelength. So don't worry that it came out negative. That's perfectly fine, because when we're looking at wavelengths, right, remember we can go up here, right? If this is 0, right, this is wavelength, right? Positive, negative, right? So essentially we just put it as 434 nanometers, and we don't worry about the negative value. So if you come out with a negative wavelength, this is the answer, 434 nanometers, right? We don't consider that to be a negative length, but when we're understanding wavelengths, that we know that waves go like this, right? They have some travel, they have some amplitude, and we can, calculate the 434 nanometers there. So, the Bohr energy shells, right? Initially, Thomson, and we talked about Thomson, we've done the plum pudding model and kind of how he thought his ideas on electrons and protons that are scattered inside of each atom. And then Rutherford came out and gave us a little better idea. And then we got the Bohr energy shells. And though it's not the best representation, I think it does help us understand these energy shells and these electrons. Just know, like, these electrons are not just sitting here, right? This electron is not just sitting, this next electron, they're at Starbucks, drinking some coffee, just chatting away. Like, that's just not happening. These electrons are spinning around this nucleus. And I mentioned earlier that we don't know the exact location of each electron, but we do have kind of an idea of where they're at, right? And this is what we call probability density, right? The darker it is here, the closer they are together, is the higher probability that that's where we're going to locate an electron, right? So here n equals 1, n equals 2, n equals 3, and it's the probability that we're going to find an electron there. There's not a high probability that we're going to find it here. There's not a high probability that we're going to find it here, right? Those are what we consider nodes, right? There's not going to be any electrons there. So we're talking about these principal quantum numbers. They do go, as we expand, and the rings, these orbitals get larger, we go n equals 1, equals 2, n equals 3, and so on. And with Heisenberg's uncertainty principle, we can't know two things with a high certainty. We can't know how fast it's going and its location, right? We can know how fast it's going with a high certainty. We can know its position with a high certainty. Not an exact, but a high certainty. But we definitely can't know both at the same time. So we end up understand this, and we consider what we call electron density. So the darker this shaded area is, the higher the probability of that's where we're going to find an electron, right? So we find a high probability of hydrogen's electron really close to the nucleus because it only contains one electron, right? So Schrodinger's equation helps us better understand these orbitals, right? And every atom has a set of orbitals. Could be one orbital, could be multiple orbitals, right? So we talk about Schrodinger's equation. This is what we consider, you're not going to be tested on this. This is what we call a Hamiltonian operator, right? What an operator does is simply directs the wave function to do something, right? Calculate this for the wave function, and that's our psi. Our psi is wave function, right? This tells us, kind of describes how the wave behaves, right? How does our wave behave? Does it behave this way? Does our wave behave this way? Does our wave behave this way, right? So that's our wave function. How is this wave going to behave? And the operator just means calculate this on how the wave behaves, right? But again, you're not going to be tested on the Hamiltonian operator, right? Energy here, this represents energy, but the energy here, this energy is equal to the kinetic energy plus our potential energy, right? So the kinetic energy plus the potential energy of the wave function. All right. So here we have positive, here we have, here we have negative, right? Now, in order to calculate probability density is that we square the wave function. Because what happens when you square something that's negative? You get something positive. Negative 1 squared, positive 1, right? Negative 2 squared, positive 4, right? So in order to get a better probability density is we square the wave function. And this probability density is where we get our information for atomic orbitals. So here we have a wave function, right? Here's our wave function, positive, negative. But if we square the wave function, we get this probability density. And I get this probability. So there's a high chance I'm going to find an electron right here. A high chance I'm going to find an electron right here. And there is a 0 chance I'm going to find an electron here. Right? We could see here, right? I'm going to find my electron, right? High probability, I'm going to find it here, 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 right? When we come out these. So n equals 1, n equals 2, n equals 3. And we're now going to learn more what we call quantum numbers. So this is the principal quantum number, right? N. N is equal to the principal quantum number. And this principal quantum number, again, lets us know how far away or how close that electron is to the nucleus, right? That describes how close that electron is to the nucleus. And these are our different atomic orbitals, right? And we can see these orbitals having different orientations, right? Like this one's going in this direction, this one's going in pointing this direction, this one's kind of pointing this direction, and we see how they have like different orientations here, right? But this would be considered, look at this here, right? We're going to look at P, we'll look at D. So this is what we consider a subshell, right? So here's one subshell. And here is, so this is subshell S. This is subshell P, right? Subshell S contains how many orbitals?
One.
One. Perfect. Yeah, great answer. Contains one orbital. Subshell P contains how many orbitals?
2.
How many?
3 of them.
3. Right? Subshell D contains how many?
5.
5.
5. And then we have subshell F, right? All these crazy shapes here. And subshell F contains 7 orbitals, right? Now, these different subshells represent these different orbitals, their orientation, the electrons that are there. So here, right, we're going to find 2 electrons or even just 1 electron. We're going to find it in one of these areas here, right? We don't know exactly where, but it's in one of those areas. Yeah, so right now, yeah, I mean, theoretically, there's more than 7 orbitals, but we have not discovered more than 7 orbitals from our periodic table of elements. So theoretically, yes, we can have more orbitals, but we haven't found an element that goes beyond the F subshell. So we talked about the first one, which is our principal quantum number, the distance from the nucleus for the electron. Now, this is an L, right? It's an L. It's not a number 1, it's an L. And this describes the shape of the orbital. Because if we look at this, they do have different shapes, right? Is that this shape is different from this shape. And this shape is also different than this shape, right? Look at this shape, right? So the quantum number L is describing the shape of an orbital, right? And in order to use these quantum numbers, what the quantum numbers provide you is the address of an electron. That is what the quantum numbers give you. So we got 3 quantum numbers that will give you the location of an electron. So I'll go over how we're going to find these quantum numbers, right? And this is M sub L, right? M sub L, it's not M sub 1, but M sub L. And this is how these orbitals are oriented, because not only the shape is different, but again, I also described it here, right? This one's pointing upward, this one's pointing sideways, and that's what M sub L gives us, right? M sub L gives us which way is are these orbitals oriented. And then we have what we're going to call spin, right? Electron spin. So electrons are negatively charged. When you put 2 negative charges together, they want to repel each other. But if one is spinning in the opposite direction than the other, well, they can coexist in the same area. So quantum number N, we've already kind of killed this idea, right? We've already gone over this and over this. Our coincident quantum number, but again, just as a reminder, any positive number, N cannot equal 0. Has to be some positive whole number. 1, 2, 3, 4. And how we get angular momentum, L, right? L is equal to 0 to n minus 1. 0 to n minus 1. That's what we got. 0 to n minus 1. So if my n is equal to 0, then my angular momentum is equal to 0 to n minus 0. I'm sorry, n minus, scratch that, 0 to 0 minus 1. Oh, what am I doing? N cannot equal 0. What am I just breaking my own rule here? N cannot equal 0. Let's scratch that. n is equal to 1, which means that L is equal to 0 to n minus 1. And here, n minus 1, n being 1, 1 minus 1 is equal to 0, so our L value is also 0. Each one of these values here, quantum number, is going to go either be 0, 1, 2, 3, and again we determine that. So let's do n. If n is equal to 4, L is equal to 0 to n minus 4, which means it can be 0, it can be 1, it can be 2, it can be 3. So L can be any one of these values. And each one of these values describes the name of the subshell. And these are the names of the subshell. They're not hard. It's S, P, D, and F. You know, this is what they look like, but you're not going to be tested on that. You're going to be tested on this. Can you calculate the quantum number L? Can you name the subshell of that quantum number? Right? SPDF. Right? Quantum, or this is L equals 0. This is L equals 1. That's P. L equals 2. That's D. L equals 3. The name of that subshell is F. So then we move on to what we call M sub L and how we calculate M sub L. So M sub L is equal to negative L to 0, and then from 0 to positive L. Well, let's take an example. If n is equal to 3, if n is equal to 3, what are the numbers, what are the values for L?
From 0 to 2.
From 0 to 2, 0, 1, 2. And if I want to calculate M sub L, I'm going to go from negative L to positive L. Negative L, if L is equal to 2, I'm going to go from negative L, negative 2, negative 1, 0, positive 1, positive 2. If n equals 3 and L equals 0, 1, and 2, well, what is our subshell? If L is equal to 2, what is our subshell?
D.
D. And D has how many orbitals?
5.
5. And if we look at these values of M sub L, 1, 2, 3, 4, 5. These are all the different orientations that are in L, or that are in D. I have 5 different orientations. Negative 2, negative 1, 0, 1, 2. All the different orientations of those orbitals. Then we get into the last quantum number, S, right? So the spin when the electrons spin around the atom, right, it can either be given, we either give it positive 1/2 or negative 1/2, depending on which way it's spinning. And there's no positive 1/2 clockwise counter. Don't worry about that. It has to either have a positive 1/2 or a negative 1/2. Not 1, not 2, not 0, not 3.5. Negative half, positive 1/2. And that is our final quantum number, m sub s. So what are the names of all the subshells if n equals 4? Well, if n equals 4, in order to name the subshells, we have to get angular momentum. So L is equal to
3.
3. So we can go 0, 1, 2, 3. And the names of these 4 subshells, 0 is
S.
S, 1 is P, 2 is D, 3 is F, and here are the names of my subshells. Now, how many orbitals are in all of the subshells? All of the subshells. How many orbitals do I have? Well, how many orbitals does S have? So we're going to go m sub L. So m sub L is equal to, for 0, m sub L is equal to 0.
0.
M sub L for 1 is equal to -1, 0, positive 1. M sub L for 2 is going to be -2, -1, 0, 1, and 2. M sub L, -3, -2, -1, 0, 1, 2, 3. So if I want to know how many orbitals are in all the subshells of n equals 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? I'm counting all of those orbitals. In the N4 shell. All right. Which of these 5 combinations? So now we can take a look at these, and we're just going to kind of cut out anything that's not valid. So we're looking for valid combinations. So here, if we're looking at A first, can n be 1? Is that a valid quantum number for n?
Yes.
Yes. Can L have a quantum number of 0 if n is equal to 1?
Yes.
Yes. M sub L, can we have a quantum number of -1 if L is equal to 0?
No.
No, right? Because in order to get M sub L, right, is -L to positive L. And if L is 0, well, that won't work. If n is equal to 3, can L be 2? Yeah, n
Yes.
minus 1. M sub L, can it be -2?
Yes.
Yeah, because we go from -L to positive L, and I have a positive 1/2. Perfect, right? If we're going to C, if n is equal to 1, can L be 2?
No.
No, because it's n minus 1, right? And then again, M sub S cannot be 0. If n equals 2, can L be 0? Yeah. Can M sub L be 0?
Wait. L can't be 0, right?
Wait, L can be,
The L would have to be 1.
if n is equal to 2, L is equal to 0, 1, 2. Oh, yeah. 0, 1, or 2. Nope, 0 or 1. What am I thinking? If n is equal to 2, L can be 0 or 1.
Yes.
Yes. And if L is equal to 0, can M sub L be 0?
Yes.
Yes. And we have negative 1/2, so yeah, that looks good. E, can N be negative 3?
No.
No. N cannot be negative 3. N has to equal 1, 2, 3, some positive whole number value. All right. All right. And 1041. All right. So yeah, this is where I wanted to end up. We'll probably get a little bit ahead of the other class in the morning, but that's okay. We talk about electron configuration. Electron configuration gives us, it shows us how to distribute all of the electrons in all of the orbitals and all the subshells, right? Subshell S, subshell, P, D, F, and electron configuration explains how those electrons are distributed in all of the orbitals, in all of the energy levels, in all of the subshells, right? And I don't teach the Aufbau principle because I don't enjoy it. This is the Aufbau principle, right? So 1s is the first energy level, and then 2s is the second energy level with 2 subshells. 3 is the second energy level with 3 subshells, SPD, 4, so on and so on. But in order to use the Aufbau principle, you have to draw it out each and every single time. Which means if you're taking an exam, you have to draw this out every single time. Energy level 1, 2, 3, 4, 5, 6, and then you go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. I'm tired of drawing it already. I don't even like it. Then you have to draw these arrows, and line them up. And what happens if you don't draw this correctly with all the arrows and line them up correctly, like everything goes to crap, right? So, and then at a certain point, it breaks down, and it just I'm not a fan of the Aufbau principle. I use the periodic table. The periodic table is how we're going to learn how to do electron configuration. Let me go back here. Electron configuration is nothing more than shorthand. Let me see if I have it here. I think I have a good, right? Here's electron configuration. So electron configuration explains how these electrons are distributed in these subshells, in these orbitals. And we can see here 1s, this is 1s, this is 2s, this is 2p, and we can see here 1s, and these represent electrons. So in 1s, we have 2 electrons. And then we can see the next one, 2s, and there's 2s, and we put 2 electrons there. That's the superscript, is the 2. And the next one is 2p, and there's 2, 4, 6 electrons, and we use a superscript, and there's the electron, right? Electron configuration is nothing more than shorthand for our orbital diagrams. Is that if I wanted to draw out, so here it is. So here's an electron, there's an orbital diagram. First energy level, second energy level, third energy level, fourth energy level, fifth energy level, so on. The first energy level, I'll give you a hint, only has 1 subshell, S. Guess how many subshells are in the second energy level? Anybody? One subshell in the first energy level. How many do you think are in the, yeah, perfect. Thank you, Daniel. There's two. And it happens to be S and P. Two subshells, second energy level. Guess how much the third one has?
3.
3. SPD. Fourth one. SPDF. And then that's just kind of where we stop. So SPD, oh, D. Actually, let me erase the fifth one here. We're not even going to get to use that one right now. So if I draw those out, here's what an S subshell has. An S subshell has one orbital, and we've seen that. If we go way back here, we're talking about quantum numbers and orbitals. S has one orbital. P has how many orbitals? 1, 2, 3. So I'm just going to use a box in order to represent those orbitals. So I'm going to draw this orbital, the S, and I'm going to draw the P. I'm sorry, P subshell. So S subshell, 1S, this is 2S, this is 2P. The third energy level, I'm going to go 3S. I know what the P subshell looks like, 3P. And I know what the D subshell looks like. D has 7 orbitals. And this is 3D. So if I want to do the electron configuration, well, let's do the orbital diagram.
D has 5 orbitals.
Oh, yeah, I'm thinking F. Sorry. Thank you for the correction. 1, 2, 3. There we go. So D has 5 orbitals. Now, if we're looking at chlorine, can somebody tell me how many atoms? I'm sorry, how many electrons? Excuse me. Chlorine has. Atomic number 17. How many electrons does chlorine have? 17. Yeah, perfect. Atomic number 17 means it has 17 protons, 17 electrons. So 17 electrons. So if I want to put those in here, I'm going to go, here's 1, 2, 3, 4. And now watch what's going to happen here. This is what we call Hund's rule, is that I need to fill this up with electrons because I need to fill this whole orbital diagram up with electrons, right? I'm not allowed to put another electron in that orbital until each orbital has 1 electron. Now that each one has 1 electron, now I can go and backfill that. Okay, Hund's rule. So I need 17 electrons. I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still have 7 to go. And now I've used all 17 electrons. So I've just drawn out the orbital diagram for chlorine. And electron configuration is shorthand for this. So what am I going to draw first? Here's 1s, 1s. How many electrons are in that orbital or in that subshell? 2. Superscript 2. I'm going to go to the next one. 2s. All right. 2s. And how many electrons are in this subshell? Well, there's another 2. I'm going to go to 2p now. 2p. And can you do this to SP? No, you cannot do that, right? I have to know each and every energy level for each and every subshell. How many electrons are in this subshell? Someone tell me?
6.
6. So now I'm going to go to the next one. I'm just going to keep going. So 3s2, 3p. How many electrons are in the p subshell for 3p?
5.
5. And this is my electron configuration. for chlorine. I didn't have to use Aufbau's principle, right? Drawing these little arrows. And now we're going to do this. Now I'm going to get rid of this here, and you should have this image in your text. Let's see here. I'm not quite sure what page this is on, but I know you have this image in your textbooks. So what we need to do is we need to kind of pretend that this is over here. I know it doesn't belong there, but we're just going to pretend for electron configuration's sake that helium is here. So the way we look at the periodic table is the S subshell can hold 2 electrons. So anything in here is considered to be in the S subshell. That's why you see 1s, 2s, 2p, right? I'm sorry, 3s, 4s, 5s, right? Everything in those two columns is considered, any electron in there is considered to be in the S subshell. Anything in here is considered to be in the P subshell because the P subshell can hold as 3 orbitals, 2 orbitals in each, or 2 electrons in each orbital, can hold up to 6 electrons. And look at this. How many columns do we have? 1, 2, 3, 4, 5, 6 columns. The D subshell, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns because the D subshell can hold 10 electrons. The D subshell has 5 orbitals, 2 electrons in each orbital. So anything in here can be considered to be in the D subshell. That if I'm doing chlorine, chlorine is right here, and I don't need the electron diagram to do this. I just need to use my periodic table. And it all starts from the beginning. We always start here. When we're doing electron configuration, we start with hydrogen. I'm going to go 1s. And if I know the maximum amount, what's the maximum amount of electrons? And, before we even fill this, I mean, before I can put an electron into 3p, I have to fill up every subshell before it. I can't just start putting electrons in P3P. It's kind of like, I don't know if you've ever seen videos of people at weddings and they stack up this champagne tower, champagne glass tower, and then they go from the top and they start pouring the champagne in and it fills up the first glass, and then the second layer, the third layer, the fourth layer, and so on, until they get to the very bottom, right? That's how this electron distribution works. So I'm going to start with 1s, and 2 electrons fill up that 1s subshell. Because 1s is full, now I'm going to go to 2s. Well, I got to make my way down here, which means that this has to be full, this has to be full, this has to be full. So 2 electrons go into the s subshell. And now I'm going to go across. I'm not going to jump. I'm going to go across 2p. How many electrons fill up the p subshell? 6. Now I'm going to go another energy level. I'm in the 3rd energy level. 3s 2. And then I'm going to go across, and I got 3p. And the number of electrons that I'm going to put in here, I'm going to count the number of columns until I get to chlorine. 1, 2, 3, 4, 5. Chlorine has, what do we say, 17 electrons? 2, 4, 10, plus 7, 17 electrons. Okay, let's do calcium. Well, calcium can be done the same way, and I'm going to begin again with the first energy level, 1. 1s, 2. I'm going to go down here, 2s2. I'm going to go across, 2p6. I'm going to go down, 3s2. I'm going to go across. Before I can get to 4s, I have to fill this up. 3p6, 4s, and this would be 4s1. This would be 4s2. So I don't want to use the Aufbau principle because I don't want to have to draw that thing out every single time. I want to. You'll always have a periodic table, for your exams, whether you're Gen Chem, you know 201, 202, is that we'll provide you with a periodic table. So it's best just to use it. The periodic table is a great tool if we can understand how to use it. An interesting thing happens when we get to something like iron. Notice what happens here. 4s, 3d. And then we don't go 3D, 3p, because we already used the 3p. Now we're in 4p. So the transition elements always cause us headaches. When we're doing the transition elements, it's always one lower than the energy level we see here. So we see here 5s, 4d, 6s, 5d, 7s, 6d. All right. So if I'm going to do iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and I'm going to count the number of columns till I get to iron. 1, 2, 3, 4, 5, 6, 3d6. This is a good tool to help you understand, but eventually this crutch gets taken away and you have to walk on your own, right? But it is a good tool to learn how to do these electron configurations. If we go to do, let's do tin. Tin is Sn, and we can do, and again, we always start from the beginning. It's always starting with beginning over here, 1s. So you start seeing this pattern, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2, 3d10, and I'm going to keep going on over here, 4p6, and now I can go down, 5s2, go across, 4d10, and I'm going to count the columns till I get to 10. 1, 2, and that is in 5p, 5p2. This takes a little bit of practice. It absolutely does. Once you're comfortable doing it on this, start doing it with just the regular periodic table. With just the regular periodic table, and you should be able to do it the same exact way, because you start to memorize, okay, anything in here is S, this is D, this is P, and you can just keep going. But you do have to follow this pattern, right? You go over here, fill that up, then go down, go across, then go down, go across, then go down, go across, then go down. We'll get to the F on Thursday. We won't talk about F today. The F is a little bit different. You'll notice here 4S, 3D. Oh wait, no, that's the one. Here it is, 6S. This here, this is where this is. So these belong right in here. So what happens, in order to count something in here, you have to go 6s, then you go 5d, and then you go 4f. 7s, 6d, 6f. We always kind of just lose we lose an additional energy level there. But again, we'll get more into this on Thursday, as well as our naming. So again, we are going to review this. It was